We start this morning session. We start with Alessandro Silva from SISSA, which will talk about dynamical phase transition and statistical excitation.
Okay, so let me start by thanking the organizers for inviting me here and for giving me the opportunity to tell you something about dynamical phase transitions and some work that has been going on for the past 2.5 years with my students, Pietro Smacchi and Anna Maraga, and Eugene Nemler and Michael Knapp. Michael is now in Munich, actually. Okay, so before telling you about statistics of excitations, I think I should spend a few slides defining precisely what I mean by dynamical phase transition. And so the setting is essentially well known. So as we have heard many times already this week, if you take a generic quantum system thermally isolated and you take it out of equilibrium, of course you do expect it, if you look at the local observable, you expect it to go at long times to a thermal state described by a Gibbs distribution with a temperature which is consistent with the initial energy density that you put in the system by taking it out of equilibrium. There are exceptions to these rules that are integrable systems, and in particular integrable systems are peculiar because they behave in a sense non-ergodically. They can keep track of the initial condition through the initial value of all the constants of motion and eventually go to a stationary state described by the generalized Gibbs ensemble, provided you keep track of the appropriate constants of motion, local, quasi-local, and so on and so forth. Anyway, experimentally, however, we know that integrable systems can be realized, but they're quite an idealization. Of course, I mean, you always have imperfections, something that takes you away from integrability. And in those cases, you expect that the dynamics of your observable will stay close to the GGE prediction for a certain time, perhaps with some renormalized constants of motion. But then eventually, at long enough times, the system will reach a thermal state. And this intermediate asymptotics is called a prethermal state, has been discussed extensively in the theoretical literature in the past years. And there are also some experimental observations, in particular in the group of Jörg Schmidtmeyer, and perhaps he will talk about them later on. Okay. So now, the physics of prethermalization is, of course, relevant for a few situations. First of all, systems in low dimensions close to be integrable with short-range interactions, like many models that have been discussed this week. And of course, the opposite limit of high-dimensional systems with long-range interactions, because in this case, you do expect your system to behave mean field-like. And mean field limit is, in a sense, a trivial example of integrability in a loose sense. Now, what do I mean now by dynamical criticality? So essentially, I'm interested in the physics of non-thermal steady states. So I'm not interested in what happens when the system thermalizes. So eventually, what happens in a real system in the intermediate asymptotics. And I will define dynamical criticality as critical behavior in this stationary or quasi-stationary state as a function of the quench parameters. So this is totally analogous to the standard Landau point of view. You think about defining an order parameter, and then you will study as a function of time its time evolution. Eventually, you will look at whether it attains a steady state or a stationary value or keeps oscillating, in which case you time average. And then, as a function of the system parameters, you do expect to see critical behavior in a similar way as what happens in equilibrium as a function of temperature, or for quantum phase transitions as a function of your system parameters. Now, there are, of course, some examples in the literature of this kind of where this kind of phenomena were discussed. The first papers that I could remember are the famous papers by Barankov, Spivak, Levitov, later on corrected by Altshuler, Yushpasyan, and company, on the dynamics of BCS like models. Later on, there were quite some studies on the dynamics of Hubbard models done semi-numerically, or actually numerically, within the dynamical mean field theory framework, or the Gutzwiller approximation, in which dynamical criticality of this type was discussed. And at the same time, Scholl and Biroli, and also Pasquale and Andrea, discussed a variety of mean field models where you will see some examples in the later on where this kind of phenomena are observed. So instead of discussing all the various aspects that were discussed in the literature previously, let me now give you straight away 2 examples and see what can happen for physical systems. So the first example is actually quite trivial, is the physics of the infinite range easy model, which is just written up here, and it's just a theory of a big spin in a transverse field. If you consider this model in the large n limit, it's perfectly mean field-like. Actually, you can solve it also for finite n. And if you're patient enough with Clebsch-Gordon coefficient, you can do quench dynamics and everything you want. Anyway, so what you will see for this model is that if you start from a ferromagnetic state and you turn on, for example, the transverse field, then of course the spin will start precessing around the new effective field, but the average value in time of the longitudinal field is going to be finite, and it's going to, well, this should be a 1, not a 2, but anyway, it's going to keep being finite for quite some time until the transverse field is large enough that the dynamics, I should not use this, but my harm, so the dynamics becomes something a bit more complicated, so the system starts precessing like this. You have a bifurcation, in which case the time average value of your longitudinal field becomes 0, and you have a diagram for the time average as Z that looks pretty similar to what you would get for the quantum phase transition for this infinite range model or things of this type. Now, a model that is a bit more rich and interesting, and that was discussed in the literature, is a large n quantum field theory. It's actually a generalization of the standard phi to the 4th model, where instead of having a scalar field, you have a vector field with n components. And of course, this model is exactly solvable in the limit of n going to infinity, and that's what makes it useful for these studies. It's also used in thermal equilibrium, actually, to make some contact with the physics of Bose-Hubbard models, but that is actually for n equal to 2. So it's pretty far from the limit I will discuss today. The physics of this model is well understood in equilibrium. There are huge reviews on this. It's a textbook subject. You can read about it in a nice review, for example, by Moshe and Zingerstein. But the good thing of this model is that, unlike one-dimensional model that sometimes are tough because of strong correlations, for this model you can think, at least in principle, to write down a quantum kinetics in terms of a systematic 1/n expansion if you just do it perturbatively. And then solve for the dynamics. It's not an easy problem, but it's doable. So you start having your tadpole, your sunrise diagrams, etc. This looks more like an egg, but what can I do? All right. So let me now describe what happens in this model at 0 temperature in equilibrium. It's again, probably most of you have seen it in your graduate studies, but still it's useful as a reference point. So if you take this model and you take the limit of n going to infinity, then of course, since you have a large n limit, you can think of decoupling this quartic interaction in a Hubbard-Stratonovich way, in which case you will get a model which is Gaussian with a mass that gets renormalized in a sense by the effect of the correlations of this field. And the new effective mass is going to be given by this expression. As you see here, it's a self-consistent equation of R for R that should be solved. It's a kind of BCS-like equation. Now, once you have this equation for the effective mass, you can immediately figure out at which bare mass the new effective mass will become 0, in which case you will have a phase transition, okay? The system will become critical. And it turns out that the value of this effective mass is, you just set R equal to 0, is given by this integral here that is finite for D greater than 1. And therefore, 1 is the lower critical dimension for your transition. And you can also study how the effective mass, which is the inverse correlation length, changes as you deviate from the bare critical mass, and figure out what are the correlation length critical exponents that turn out to be given by these two expressions, depending on the dimensionality. So above 3 dimensions, you have the mean field result. So, yes?
A negative mass?
A negative mass?
Yeah, but
Yeah, but it's okay.
I mass squared is negative as a space.
Yeah, it's okay. Now, suppose that now you consider the problem out of equilibrium. As many things in quantum quenches, the first study out of equilibrium was actually done by John with his student Spiros Soteriadis. And what he considered is actually what happens when you take, when you make a quench from some initial R0 bare mass to some final one. So today I will discuss only quenches from the disordered phase. So I will focus just on this particular problem. And in this case, not surprisingly, instead of getting just a given value of your effective mass, you will get a time-dependent equation that determines it, which is given by this expression. So the effective time-dependent mass depends on the correlation function, equal time correlation functions of your fields. And you can easily solve for this if you write down your fields in terms of the mode operators that diagonalize the initial Hamiltonian with these amplitudes f of t that turn out to satisfy this nice equation. So in practice, if you want to solve this problem analytically or numerically, what you have to do is solve this differential equation coupled to this integral equation. Self-consistently. What?
Before was lambda over 12. Now it's lambda over.
It might. I didn't.
Is a deep meaning.
Is a deep meaning? Actually, I don't know. Honestly, I have to check.
Change of normalization, I suspect.
It's probably related to the fact that here I'm writing the equation. Where is I should no. You see here I'm writing the equation. I'm spelling out what is this. Well, here I'm keeping it unspecified. So the moment you calculate this in equilibrium, you will get the extra factor of 2 that gives you 12. So anyway, but I should check this. I don't remember it by heart. Anyway, so you should solve this equation. So this was done actually both by Pietro and Anna quite efficiently on a computer. And what you see, for example, if you make a typical quench, well, this was first done by John and Spiros, but we redid it since we wanted to study this problem, is that your effective mass initially keeps oscillating like crazy, but then eventually goes to some stationary value at long times. And if you now start from so you make a quench and you start decreasing and decreasing the final value of your bare mass, this I think is in 3 dimensions, 3 and 4 dimensions. We always study 3 and 4 dimensions because in 2 dimensions you don't have anything interesting in this problem.
Unit of R0?
This one it's actually quite arbitrary because it depends on what is the initial value of your mass. So it does not really matter to normalize it.
Shall I give really meaning that is so teeny the region, or is completely arbitrary? It's interpreted. Can be the age of universe. I don't know. I mean, what is the scale?
The scale, I think it's R0, the scale, but the scale of what? I mean,
Time.
the time scale.
There seems everything happening in very, very short time, then nothing.
Up to 20, I mean, it's not really short.
Sure, but I mean, the obvious.
No,
what
20
20 means.
One is the unit of, depends if you put something in front of this.
Well, I would have to go back to the paper, but initially, I mean, typically we set some R0 which is equal to 40 or something, and we make a quench. We don't really check at what, I mean, we are not really interested in this transient behavior, so we do not really check what is the time scale at which you attain the stationary state. So
Depends on the value of the cutoff too.
yeah, it's related to the cutoff, to the final value. It depends on how you put the cutoff. If you put a smooth cutoff, you get different oscillations. If you put a hard cutoff, you get hard oscillations. So, I mean, I wouldn't give too much meaning, physical meaning to this transient behavior, because indeed it depends okay, Andrea's complaining because he did a paper about this, but anyway, it depends on the cutoff, how you put the cutoff. So what I'm going to describe today is the physics of what happens at long times and where you attain the stationary state. So in that case, everything is pretty under control. Anyway, so what happens if you now start decreasing your final value is that your stationary effective mass keeps decreasing and decreasing and decreasing and decreasing, and eventually you will be able, also out of equilibrium, to find a critical bare mass at which, bare final mass for your quench, at which you hit a dynamical phase transition. The effective mass becomes zero in the stationary state. Now, can we predict analytically what will be this value? Luckily, John and Spiros formulated a nice ansatz to predict the stationary value of this effective mass, which is written up here. Actually, this ansatz conceptually is based on the following. You essentially solve the problem with lambda equal to 0 for your correlation functions, phi squared, and then you time average them, okay? And you pick only the stationary component. And then you replace with the bare mass, you replace the effective mass R star. And that's the equation that you get. Now, this equation is quite important because now we can really predict where the critical point is going to be. Well, first of all, it works pretty well. We checked it in all possible cases. I mean, we did really a lot of simulations to see that it's valid. And then it turns out that you can really use it to find out where is the critical point. You just set R star equal to 0, and you get this integral, which is finite for dimensions greater than 2. So 2 is now the lower critical dimensions, and the critical exponents turn out to be given by these expressions. Now, there are two things I want to say at this point. First of all, these are the same exponents that you would get for a thermal transition at finite temperature. So if you would change temperature and heat a thermal critical point. The second observation is that, of course, here we are doing a quantum quench, so you could think that perhaps if we do some other protocol and change parameters in a different way, we will get something else. It turns out that this is not the case. For example, you can solve semi-analytically the problem of a linear ramp, in which instead of going abruptly from R naught initial to R naught final, you do it on linearly with a certain time scale tau. Now, this figure here is supposed to show you that if you fix your tau and you change your parameters, of course you will be able also in this case to hit a dynamical critical point at which the stationary value of the effective mass is equal to 0. And of course, as you go below this dynamical critical point, it's going to stay 0 in the long time limit. But of course, I mean, you cannot make much progress if you don't know how to calculate, at least analytically or semi-analytically, your critical point, because you want to calculate what are the critical exponents at least. And luckily, it turns out that the problem is still similar in spirit to what was done before for the case of a quantum quench, with a minor difference. So you still have these two coupled differential equations, but while before R naught was a given number, now it turns out to be a function of time, a linear function of time. Now, in principle, you can solve it on a computer, but if you want to predict the stationary value of your correlations, you can use the same logic as before. You solve the problem for lambda equal to 0, then you let the system evolve after the ramp, you time average your correlations, and then you pick only the time average solution, and that's what you will get. So these are the values of these functions that are attained right after the ramp. So I ramp and I stop and I pick up this value. Okay, so it turns out, we checked it very extensively, that this ansatz works pretty well, but it turns out to work provided you renormalize in a certain way also the ramp duration. So we were able actually to map out tau tilde that depends on tau for different lambdas numerically. And it turns out that this relation is linear for both tau small, close to the limit of a quantum quench, or tau very large, in which case you have really a very, very slow ramp. This is important because in that case, since this relation is linear, I can really predict what is my critical point by essentially putting r star equal to 0 here, taking the expansion for large tau and small tau of these functions. They turn out to be expressible in terms of Airy functions, and work out the expansions, I mean, analytically. And actually, I forgot to write it up, but what you see is that if tau is small, then what happens is that, well, this doesn't make sense. Tau over some time scale is small. Then what you have is that your R critical is going to be essentially the R naught, the R critical that you get for a quantum quench plus corrections that go like tau squared. While in the case of tau large, then you will get that your R critical is essentially the same as in equilibrium, plus deviations that go like 1 over tau to the 2/3 in 3 dimensions, or 1 over tau in 4 dimensions. Anyway, the problem is, whatever you do, you calculate your critical value for your bare mass, you will find the dynamical phase transitions, but the critical exponents are still thermal. And therefore, we have a situation in which we do some calculations, and whatever we get looks like a boring thermal transition, at least for large n, both for quenches and ramps. Now, I have many ways to describe this situation, but the way I'd like to use today is as if you're driving your car in Italy in the summer, and you stumble quite frequently on a Roman bridge. And if you look at the Roman bridge in daylight, it's actually the dullest object on Earth because, well, it's quite boring. But if you look at it in the proper light, it's actually quite beautiful, and you really see that it's a work of art because the arches are perfectly semicircular, they form perfect circles, etc., etc. Now, it turns out that this problem is similar. Perhaps what we are seeing is just a boring phase transition simply because we are looking at it in the wrong way. And what we have to find is what is the proper way to shed some light on the dynamical nature of what we're looking at.
It's correct to think that the result you get is, imagine I don't do dynamics. I just do the usual thermodynamics on this system with time complex, though, imaginary. And so I have a phase transition. So I got this result, then at the end I just turn IT.
Well,
I observe this.
So let me explain it to you in my own way that perhaps is similar to what you're saying. So since you're putting a finite, so the phase diagram at finite temperature for this system would be something like this. So you would have a thermal, this is your quantum phase transition, this is your thermal phase transition. Now, instead of temperature here, put energy density, which in equilibrium is more or less the same thing. So energy density, rho of epsilon. And this is your R, okay? So now, what happens is that as I start decreasing and decreasing the final value of my bare mass, what happens is that I'm increasing and increasing the energy density that I'm putting in the system. So it's as if I'm moving actually in this direction. So it's not surprising if you think about it in this way that you will get a thermal transition. But still, you know, the occupation of modes is not thermal at all. There's nothing thermal there. I mean, the system is not able to thermalize, and so therefore, this is true, but with some caveats. I mean, it's not really appropriate. Anyway, so you can try to shed some light on this problem in many possible ways, studying correlation functions as Andrea and collaborators have done, or perhaps entanglement evolutions. The way that I prefer, that's because it's my taste, to study the statistics of observables, because it turns out that the full statistics of observables typically gives you a lot of information about the physics of non-equilibrium systems. And in particular, in this case, we were really inspired by experiments that can, in principle, be performed with cold atoms. So in particular, we had in mind the following protocol. We don't know whether in the three-dimensional Bose-Hubbard model there is a dynamical phase transition of the type I'm discussing. Yet, imagine taking a system in the Mott insulating state, represented by this diagram here, and then quenching it towards the superfluid parameters and stay there for a certain time tw. And then you go back. Now, of course, when you go back to the Mott insulating state, you will have created a bunch of defects as compared to the initial perfectly regular array, which will be essentially doublons, holes, and whatever. And experimentally, it turns out that with nowadays techniques, you can count them. And you can pretend to repeat this experiment many, many times and generate full statistics for the counting of these defects. And the question was, when we started this, is this statistics giving you some information about the fact that you're close to a dynamical critical point or not? So the answer that is not based on the Bose-Hubbard model, but based on calculations with the ON model in the large N limit, so I just want to make a precise statement, is the following. In that case, if you make a quench and stay for a time tw in this phase, and look at how the fluctuations of the number of excitations grows in time, what you will see is that if you are above this dynamical critical point that I discussed, these fluctuations will always saturate. At the dynamical critical point, they grow logarithmically, and below the dynamical critical point, they grow as a power law that depends on dimensionality. The logarithm does not depend on dimensionality. It's always there in 3 and 4 dimensions, always the same log. Okay, so let me now show you how to do this calculation. You essentially think about the same calculations that we have done before, but instead of doing a single quench, you make two quenches, a double quench. So you stay with the final value of the mass for a certain time tw, and then you go back. And when you go back, what you want to calculate is the statistics of excitations, of the total number of excitations with respect to the ground state with the initial value of the bare mass, which is given by this number here. Well, this turns out for this problem to be exactly, I mean, the moment you know what is R naught, you can compute it exactly. And it's given by this expression. So this is essentially your generating function, where this rho k tw is essentially the occupation of these modes in the state that is obtained by waiting with this final value of the mass for a time tw. So it's just the mode occupation and nothing else. Okay, so now, of course, I mean, you can compute this for a Gaussian model, and just to use it as a benchmark. And for a Gaussian model, the calculation is quite boring, because in the free case, you know what are these rho k tw. You can compute the full statistics easily. What you obtain is that if the final value of the mass is not equal to 0, so if the model is Gaussian and massive, then all cumulants saturate to finite value. And when it is equal to 0, they all grow with different power laws depending on dimensionality. It turns out, so now you can do the same calculation now with a finite interaction. And what happens is that with a finite interaction, the average value of excitations actually turn out to always saturate. Again, these oscillations have the same peculiarities as the one I was mentioning to Giuseppe before, and they depend on cutoff, etc. But the time behavior after essentially a few time units turn out to be, to be just oscillatory and around some finite value. Now, if lambda is not equal to 0 and we are in 3 and 4 dimensions, now let's compute the fluctuations and make a quench at the dynamical phase transition. We can hit precisely the dynamical phase transition thanks to these ansatz that I described before. So we know precisely where it is and we can easily hit it. And what we see is that in 3 dimensions, if we calculate the fluctuations, you see that they just grow for different values of interactions, different values of initial parameters, etc. They just grow all logarithmically, nicely and logarithmically, as represented by these straight lines. This is actually something that happens also in 4 dimensions. As you can see here, it's actually much nicer in 4 dimensions, the figure. And it's a peculiarity of this dynamical critical point. We don't see it anywhere else. I mean, just at the dynamical critical point. When instead of doing a quench at the dynamical critical point, you do it above the dynamical transition, then what you will see is that your fluctuations seem to be following this master logarithmic curve for a certain time. But then eventually, look at the scale here, is 200, before was 20, the scale of those oscillations, okay? But at a certain point, they detach from this master curve and then saturate. So this is what happens above the critical point. Of course, the closer you are to the dynamical critical point, the more these curves follow the master curve before saturating. And instead, if you go below the transition, what you see is that the fluctuations grow as a power law. In 3 dimensions, it's linear. In 4 dimensions, turns out to be quadratic. So it really depends on dimensionality. And actually, we can compute it, well, we can predict it based on the scaling of this mode occupation as a function of alpha, which turns out to be different in 3 and 4 dimensions. So let me not spend too much time on this. Anyway, I think I run too fast, but anyway. So a couple of comments. I mean, all of this is, unfortunately, all of these time-dependent calculations are unfortunately based on just numerical calculations. I mean, we just take these equations, we solve them on a computer, we just know analytically how to predict this critical value for the bare mass, but we do not know yet how to derive this logarithmic growth on the power or the power law growth, etc. Simply because, well, it doesn't seem to be, at least, well, we didn't find a simple way. By the way, we don't know, perhaps John knows, but I don't know how to prove the ansatz at the moment. I mean, I know how to justify it because it makes sense, but in both cases, it seems to work very well, but I don't really know why it works so well. So that's really something we should figure out in the future. Anyway, so one thing I wanted to mention now is that, of course, I mean, you should not expect this kind of behavior to be generic. For example, if you take the infinite range easy model, which does not have any space structure, so there is no k, no momentum, nothing, it's just a single spin, you can, of course, calculate the full statistics, for example, of the longitudinal field. In this case, it's just given by this function. And I mean, this is the generating function. You have to take derivatives, logarithmic derivatives to get the cumulants. But what you see here is that, I mean, as a function of time, there is nothing. You just take your fluctuations will oscillate as the average. And when you take a time average, you will get singularities, which instead of in the derivatives, exactly as for the average. So there is nothing peculiar in this case. I mean, it's just a boring model. Nevertheless, just to, since I have some time, I have time to discuss something that I think is important. this model allows me to make contact with a different notion of dynamical criticality that was put forward in the literature, in the recent literature. So we have seen yesterday in the talk by John Cardy that when you look at this amplitude, which is nothing but a return amplitude, I mean, you take your initial state, you time evolve it, and then you overlap it with the initial state. If you think about IT as R, as a, you know, think about making an analytic continuation, this is nothing but, in a sense, a partition function in a strip. And as such, you can think of writing it as e to the minus n is the number of degrees of freedom in your system, times a free energy density. And this is something we used quite extensively with Andrea in order to compute statistics of the work and things of this type. Now, a few years ago, Stefan Kerain, Markus Heil, and Anatoly Polkovnikov suggested that since this return probability has this amplitude has this form, then if you're able to see zeros of z of t, which would correspond to singularities of this free energy, this would correspond to some kind of critical behavior in your system. And in particular, they calculated the behavior of this function for the transverse field Ising chain for quenches across the quantum phase transition, and it happened to that in those cases you were getting this kind of singularities, and well, they call this dynamical criticality, and I'm not saying, I mean, this is, of course, I mean, it's an appropriate name, but the problem is that unfortunately in later works people have calculated this quantity for in many other cases, for example for quenches within the same phase or across the phase transition for various models, and sometimes you see these zeros, sometimes you don't, and you don't really know what is the physical significance of the presence of singularities in this large deviation function. I mean, how to connect it to the physical properties of your model.
If you take this interpretation of partition function,
Yes.
or complex value of t,
Yeah.
well, you should expect to have the zeros of Yang-Lee.
Absolutely. So that's what they were discussing. So their idea was essentially based.
Because you analytically continue.
But yeah.
System size.
So what is the variable you are analytically continuing? This I don't understand.
System size.
The slab.
The thickness of the slab.
This is the thickness of the slab. You see,
Temperature, and it's not.
is not temperature.
It's the partition function in a bounded geometry.
If I have a certain singularity one variable, I just rotate it.
Yeah, but what the variable you rotate is system size. You make system size complex.
That's exactly what I was doing.
That's what John mentioned yesterday.
Yeah.
Anyway, so since I did not fully understand this idea, we tried to make the connection to see if there is any connection between this notion of I mean singularities and criticality, etc., and the more standard notion of dynamical criticality that I've been discussing today, which is, in my opinion, is quite standard and understood. I mean, there is nothing very very strange there. So in particular, if you take this infinite range easy model, then you can think of taking your Loschmidt amplitude, and you can exactly compute it. I mean, there is no problem. It's given by this overlap here. This is essentially your initial magnetization, and this is the magnetization as a function of time. Of course, this is valid in the large n limit. And so it turns out that, for example, if you make a quench from zero transverse field to some finite transverse field, and you plot, as it is done in this figure, the longitudinal value of the field, you see that it's 0, 0 of the magnetization. Sorry, I apologize for the different notations. you see that it's 0, 0, 0 up to a certain value, and then it becomes finite. The figure is pretty similar to what we had before. Now let me plot instead the minimum of this g should be a z of z squared, the z I defined before. And it turns out that as, in this case, you get 0, 0, 0, 0 up to a certain point, and then you get something finite. So it essentially seems to follow the presence or absence of this dynamical phase transition. And, well, when we did this simple calculation, we were very happy. We thought we finally understood what is the connection, what is behind this. But actually, it turns out that this does not work, because if you make a quench, for example, from a different value of transverse field, it turns out that you never have those singularities. I mean, you don't get them. And actually, if you go a bit deeper in your model and you compute the effect of quantum fluctuations or finite size effects, since you can do it, it turns out that these singularities, these zeros of z, do not survive. So, in my opinion, this tells us that, unfortunately, the problem of understanding whether there is, whether this notion of dynamical criticality, I mean, what is the meaning of this notion of dynamical criticality is still open. So now, coming back to some kind of conclusions, now, I've been discussing the fact that you can think of observing some features, some dynamical features of these dynamical phase transitions by looking at the statistics of excitations. Now, of course, what I've been studying is the mean field limit, which is quite ideal. And in particular, in real systems, this phenomenon will be observed at most in the pre-terminal state. So if one will observe something that grows logarithmically, it will grow logarithmically only in the intermediate asymptotics, then eventually it will saturate, because you have to go to the terminal state. But still, the time scales might be long enough, as in the experiments by
I
Johan.
understand. You mean even the thermal state can be critical.
Yes, but in the terminal state, I've shown you the calculation before. Nothing changes in time, so then it's quite boring at the terminal state. Now, the most important observation that is made by a number of people is that, I mean, of course, I told you that the critical exponents for the dynamical transition and for the thermal transition are the same in the limit of n going to infinity. I don't know whether they are the same in a 1/n expansion. So in principle, you could see some signatures also with standard tools if you do properly the calculation in a 1/n expansion. Unfortunately, this calculation turns out to be quite nasty, because what you have to do is write down the quantum kinetic equations, and then you cannot pretend to study them in the long time asymptotics, because that's thermal. When you take 1/n corrections, you expect inelastic scattering to lead you towards a thermal state. What you have to do is be able to identify the pre-thermal state and study the behavior there, which is quite tricky. So, but whether you will see something or not depends on whether you will be able to identify this intermediate asymptotics in your equation. So I think I finished a bit in advance. So I would like to thank you for your attention.
We left the right time for question, so not in advance. Giuseppe.
I don't know if you know the answer, but let me ask.
If I don't
How your approach of treating these dynamics, that essentially you do self-consistent approximation. I'm talking 1/n.
Yeah.
So essentially you treat it like Gaussian model with gap equation in it.
Yeah.
Right. So how does this approach compare with something that, for instance, I've been doing with Andrea De Luca for a while, that instead we treat everything semi-classically, and the interaction we treat interaction. So we have a different
You do
approach.
semi-classics.
Yeah. You have as well a dynamical equation, a model. You get easily prethermalization, you get a lot of
No,
phenomena.
I understand your question.
A gratis, to say, but how the two compare?
Well, Okay, so semi-classics, I mean, your semi-classics should be valid for large occupation of the modes, right? This approach, I think, does not have that constraint, I mean, this large N expansion. So, but there might be some limit in which they touch each other. So I'm sure there is. It's just, I mean, your approach would be valid for large quenches, I expect. So for quenches in which the occupation of modes is such that the expectation value of the fields is I mean, is
Yeah, but
significant.
in the same times you treat the interaction proper as interaction, not as a fake quadratic.
Well, but this is, I mean, it's okay. I mean, it's fake in the sense that you don't have inelasticity. So in that sense, it's fake. But in all other respects, it's quite fine. So what I mean, 1 over n corrections will give me. Why, Fabian, are you complaining?
No. I mean, large infinite n is infinite n. I mean, that's.
Yeah, infinite n. So I'm you know,
How
I
generic-
wrote down the rules of the game at the beginning.
No, I completely agree. But so I was making a face because 1 over n corrections. I mean, who knows what they will do?
No, I disagree with what you said about 1 over n corrections. But anyway, go on.
No, I don't have. I mean, I don't have any other statement to make. So if you
Can I make one?
if you want to disagree, please.
Well, may I? Yeah.
The sure.
Well, I don't think that. I mean, I think the reason that the self-consistent equation for critical point works is precisely because after a few initial oscillations, this effective mass settles down to more or less a constant value, right? So, although in principle you should average over the whole history of the system, you can ignore these initial oscillations, and that was the basis of our approximation. So that's why the large N equations were almost. I know that the kernels aren't quite the same, but the reason that you get the same critical exponents at large N is because the mathematical structures.
Yeah, no, with that I agree.
Now the 1 over N, you say they will eventually thermalize, but I would guess that that's non-perturbative in 1 over N, and that
I'm not sure.
and that you can in principle do 1 over N corrections or even do epsilon expansion, and you'll get something interesting. And I doubt if the
You
exponents.
see, I'm not really sure, because the moment I write down a Boltzmann-like equation with 1 over n corrections, I mean, the moment I include a sunrise diagram, that's inelastic scattering. I truncated it.
Oh yeah, I agree. It includes scattering, but to see thermalization out of scattering, that happens at
no, but
enormous times.
no, but
Out of weak scattering, which is what you're saying.
yes, but the moment I plug it in a kinetic equation, so I treat that as a self-energy insertion and I plug it in, so it's like having it as a collision kernel, so a finite collision kernel. And a finite collision kernel will, you know, typically when you put a finite collision kernel in your Boltzmann or Boltzmann-like equation, then immediately you get as possible solution the Boltzmann, I mean the Gibbs distribution. So that's why I'm a bit hesitant.
So I think if you work at large but finite times, then there is a sensible
Yeah,
1 over
absolutely.
n
Yeah,
expansion
yeah, I agree.
to be done there.
So there is a time scale which is smaller than n times something,
Yeah.
for which you have this intermediate asymptotics, and you will be able to essentially expand systematically around this point
That's
that
the
we are
interesting
discussing.
calculation.
And this is the interesting calculation. I'm just saying that, I mean, what I've been trying to say, and perhaps did not succeed, is that one should first identify this time scale, then go before this time scale, do intermediate asymptotics, and there calculate critical exponents, statistics of excitations, etc., etc., etc. Andrea. Oh, sorry.
Self-chair, it's okay.
Now going back, I mean, to the things that John was suggesting, actually we looked at the epsilon expansion with my student for another issue. So basically we treated this this dynamical transition, it is associated to a fixed point renormalization group, so we included the fluctuations at the first order in epsilon. It turns out that the exponents, they are still the same as they would be in the thermal case, but the fixed points itself, I mean, so if I look at my fixed point in the parameter space due to the dynamical transition, and I try to map it in the fixed point that would have a finite temperature, they are not, I mean, although they give the same exponent, they are not the same point.
Well, to order epsilon, somehow things are still pretty universal, yeah.
Yeah, but you know, that's true first, and so the exponent is the same, but the fixed point is not already at there.
Okay.
So,
Well, the value of the fixed point depends on the way that you renormalize the theory anyway. So.
yeah, no, but in principle, so in one case you have the quench parameters, the other you have the temperature. You can try to establish a map between temperature and quench parameters in such a way that should overlap. You never manage to do so. So it's strange.
Yes.
May I just to change the subject about the zeros of the return amplitude, just so it's absolutely clear. In what I was saying yesterday, I was looking at a quench from the disorder to the critical point, and there I clearly identified the zeros as being something to do with quantum revivals and within the quasi-particle interpretation, which I didn't explain, but I completely understood. So whether that's true in general, I don't know.
Yeah, okay. Thank you.
Are there more questions? If not, let's thank Alessandro again.